Mm.
I have
Okay,
started already.
okay, okay, great. This meeting is being recorded. I'm sharing a screen. Let's go to. I thought this might be somewhat interesting for some of you. And so I thought I'll talk about a little bit on teleportation. And fortunately, nowadays there are some Python modules using which you can actually teleport a quantum bit, a qubit from one place to the other. Of course, within the machine. It's not something. Nowadays, there has been a lot of progress overall that you can actually make video conferencing. There are several things that have been worked out. So via satellite stuff, etc. I will be talking about them around the end of the lecture. But we can do something funny. Instead of going at that high-level technology stuff, you can actually sit in your room and run a small, like teleportation stuff over the internet in an actual quantum computer, not like a simulator. IBM has those facilities for literally anyone. You just have to create an account with your IBM Quantum Lab here. You can see here. And to run your code and to prepare and check your code first in the simulator. Sorry? Sorry? Okay, I guess I need to mute everybody and then unmute myself. Okay. So what I'm going to do is, how do I mute all, and then, okay, I think I'm unmuted. So let's share the screen again. I guess you can hear me, right? Can somebody just unmute himself or herself and confirm that you can hear me?
Yes, we can.
Yes, sir.
Oh, great. Okay, perfect. Okay. So you can just do this pip install Qiskit. I don't know the full form of Qiskit. I have no idea. And this circuit is something probably some of you may be familiar with. This is the standard circuit that I have just copied from Nielsen and Chuang's book. I'll be referring the book later on. So this is something that we studied in our MSc Masters, and then at that time it was something like a dream. We learned that quantum computation, specifically teleportations, are possible, but there are issues with decoherence and stuff like that. But within 5 or 6, 7 years, there has been a really, really massive progress in this area. And now this is something people are able to do on more than 100 kilometers earlier. And now they have teleported bits from Earth to satellite and back, and one can do some conferences and things like that. Okay. The first question is, what do you think? So forget about quantum teleportation. First thing is that quantum computers. Do quantum computers exist? You can go to menti.com, use this code 6740805 and let your cast your vote. I will get to know how relevant my talk today is, or in what pace I should actually proceed. This is important because if I see that most of the people already know some of the stuffs, then I can gear up and spend more time on somewhat which is more technically advanced. And if I see the audience is not that much familiar with all these stuffs, then I can spend more time in the basics, depending on what you want to hear. So please let me know what do you think, yes or no or maybe. So in general, can somebody unmute yourself and let me know, what do you think? Do quantum computers exist or not?
Sir, physically it is not available to you, but we can work in a cloud, IBM Quantum.
Right, very right. Yeah. So it is not commercially available in that sense. When you said physically, it actually exists somewhere. You can see the background, in the background of the screen, something is fading in. And that's the image of a true quantum computer. And actually there, not only this one, there are several variants of quantum computers. But every quantum computer has several different limitations. For example, some are, I mean, most of them have similar, but definitely depending on their technology or things like that. The main problem that every quantum computer, I guess, faces is the problem of decoherence. It's the same, I mean, and then error correcting codes and things like that. This image that you are seeing, this is one of the ways to achieve a quantum computer. This has been done by IBM. They have a lab. They have several such quantum machines, quantum computers. And you can see now. So this is this box part. This is here it is actually. This is the quantum computer. The qubits are sitting over here. This is the chip, the qubit chip that is sitting over here. And the rest of the stuff is somewhat like to isolate it from the environment so that it's near the absolute zero temperature. Because we don't want any thermal noise to alter our final result, right? So we need all the thermal noise to suppress and all other mechanical or vibrational noises to suppress, right? And so also electrical or external fields, everything. So this needs to be cooled down to a very low temperature. All sorts of cryogenics and everything. And cryogenics itself as a technology has its own issues. So it's very complicated. So yes, the physically actually these are the qubits that sit over here, somewhere here, where my mouse is now, mouse cursor, and the rest of the stuffs are to perturb the bits and make measurements, etc. Because ultimately you have to you'll have to interact with the system, right? Otherwise you won't know what is the state. So yeah. Okay. Yeah. So this is the actual chip that you were seeing here. I just want to know how many of you are already aware of this. So should I spend some time on this or not? So do some of you know how does this chip work, or I mean, what exactly is here? Where are the qubits in this image?
Sir, we don't know about this.
Okay, so essentially these are the qubits that you see here. Let me annotate it. And okay, so essentially these are the qubits. This one. And what is happening is essentially these are the substrates. These are substrate materials. These two different substrates. And there is a very small nonlinear Josephson junction. You can see it here. Here, this one. And the idea that they have been chasing is something like you have some equal balance of electrons in the two side of the nonlinear wafers. And okay, and if you perturb the system externally, then whether the electron has moved, I mean, when there is a current that is moving through this Josephson junction, it creates a magnetic field, right? So now you can go back to your class 11 or 12, or maybe in BSc classes. You remember the LCR circuit, where there was an inductor, there was a capacitor, and small resistance maybe. And if there is no resistance, it keeps oscillating between these two. So it's something like that. You load some amount of charge in the capacitor, suppose, and let it oscillate. If there is no resistance, if it isn't something like an ideal stuff, then it will keep oscillating between the two. So essentially, this is something that I'm giving you a classical analog. This is quantum, because here actually an electron is moving. So the level of accuracy you'll have to identify is whether the electron has passed through or not. That's someone was telling. I was attending some conference, and someone very, very accurately said whether the electron has passed through the bridge or the nonlinear Josephson-Janssen or not. That's something really interesting. But there are several other ways. This is one way that is IBM is approaching. Probably they have used several other paths also previously. But in general, lot of different independent thoughts are there, and they have been experimentally verified several ways in several laboratories, and there are a zoo of method that allows you to create such qubits, and every method has its own benefit over the others. So it's not something this is the best. But for now, as far as I know, of course, my knowledge is limited because I'm not an expert in this field. I don't work in this field professionally. It's something that is amateur for me. But in general, whatever, as far as I know, this is one system which IBM has created and has opened it for public. So wherever you are, as long as you have a connection to the classical internet, you can create an account in whoever you are. You don't have to necessarily hold a PhD degree for this. Whoever you are, you can create an IBM account, you can get an IBM ID, you can log in, and it's suppose Python. So you can, there's some variation of the Python algorithm that I'm going to discuss about. And you can write your own code in Python, given those, you are using their libraries, etc., etc., etc. And you can submit your job in their machine, and it will be, so through your classical computer, classical internet, you can submit the job, and it will be in their IBM cluster queue, and it will be executed, and then you can get the results. And when the result comes, again, it comes through your classical internet on your classical computer. But it will be executed on actual quantum computers. This user facility is something I am not aware if there are any other companies who have done it. Maybe, I'm not sure. So at least this is something that I know that you can do it with Python. So I thought this is something that would be interesting for some of you, at least if you guys have assembled here to learn something on Python. And these are very simple. I mean, you don't have to be a very, very great coder in Python. I myself I'm not someone who is a really master of Python coding, because I never used Python earlier. I used to use Fortran. So yeah, okay. So to teleport a bit from something that I've to teleport this bit. So this is one quantum state. So this one with something like 0.7, root of 0.7 plus root of 0.3. So this is in some superposition of two states. I'm going to explain what is 0, what is 1, etc. Don't look at this code now. You don't have to read it. You can treat it like this. This is the slide, that is the last slide of this presentation. We will come back. And it has several bits. You can see here different colors. We will try to understand the individual components of this whole code first throughout this lecture. And when we will learn this, so this is the trajectory of today's lecture that I'm giving you. When we will finish learning all these things, we will put together the whole code, and then we will run it on a quantum computer to see whether we are able to actually teleport one bit, one state from what I've written here, from Alice's state to the Bob's qubit. Okay, so you can go to the Qiskit course lab. I'll be giving you much details about the future, about the references of this in the next slide. So don't worry. So again, this is the slide. If some of you are already familiar with the Nelson Chuang book, you probably will recognize this figure. This is something like a very famous figure of quantum teleportation. Okay, so let's go to the next slide. Resources, as I promised. This is the best book that I am aware of, but definitely there are many other books. And if you go to YouTube and search for quantum computation resources, there's been several nice videos on which book to read, which book to start with, etc., etc. I personally, when I was in my master's, I read some first of the few chapters of this book I have read. And this is something which is very promising, but unfortunately, yes, at that time, decoherence or decorrelation was really a huge problem. So, but nowadays, this is something really improving very well. Again, disclaimer that I'm not an expert in this field. I just partly read, so there can be several things that I'm saying wrongly or something. If you find somewhere I'm making a mistake or my statements are not very true, feel free to rectify me. Unmute yourself and just tell me. I'll be very happy to learn from you. Hands-on computation, again, as I said, there are many available platforms. This is not a place to promote IBM or anything. Feel free to explore other available resources too. I'm sure that they are really good, and this is one that I'm aware of. That's what I'm just presenting. It's not the best. I'm not claiming that. It's very user-friendly, that I can tell, definitely. They have made it really interactive textbook. If you go to this link, you'll find a really very interactive textbook. You just need to click and go next, and you'll be able to read it. While reading, you can actually go to this tutorial also. They have a very nice Qiskit channel where they periodically hold several interactions, etc. And right, while reading these references, they link it with your IBM ID if you have one. If you just open one, it's free, open to all. You can log in and you can actually try running those examples. What I'm going to do today is covering only some part of their first 3 lectures of this YouTube channel. So mostly this will be based on the lecture notes by Elisa Baumer and the lab they have presented and their curriculum, which is presented here. Okay, I'm not going to do something new, something very different, or something which is a research topic that I have done, nothing like that. Basically, I'm reiterating, and I very strongly recommend you that to go to this YouTube channel and attend the summer school they have organized. This is definitely going to be a very incomplete description of quantum computing, because in 1 or 2 hours it's impossible. So I'm not going to try that. I'm just going to try to show you something which is very simple, basic, and probably interesting. Okay, so now let's go backwards and look at the little bit of elements of classical computing and quantum computing. How are they different? So as we know that in classical computation, we talk about the bits, which comes with 0 and 1. I found a nice way of saying, look at this. This is something, 1 bit. It can be white and black, and it can have white on up and black on down, or black on up or white on down. So if you call it a 0 and 1, so this is something like a one out of 2 to the power n possible permutations, this one. And if you think of a quantum bit, it's something like the coin is on the air. So it's, you don't know, you only have probabilities when it will fall, when it will collapse in one of its states. But there is no guarantee. You don't know when it will fall. There can be some something in the surface, and then it can flip it or not. But only bits are not the bits of a computing. You have to have some notion of gates as well for computation. So that the gates are very important to perform some operations on the bit, so that you can flip a bit or do something else, add 2 bits, etc. So there can be 2 types of gates. One is, as you know, a single bit. A gate that is operating on a single bit, which is a NOT gate. For example, if you have 1, it just turns it to 0. Okay? And so similarly, in the quantum mechanics also, you have several qubits. Funnily, interestingly, Pauli matrices are those beautiful, act as the gates for these things, for these states. And of course, there's a very, very important stuff, which is the Hadamard gate. And you know about OR gate, AND gate, XOR gate, or things like that, right? So if you have something like an XOR gate, this is something in the 2-bit. In the quantum computing, something equivalent to the C0 gate, but I should not call it equivalent. It's because XOR gate is irreversible, and quantum mechanics fundamentally has to be reversible. So all the operators have to be unitary. So C0 gate is somewhat effectively gives you the similar flavor, but it has some subtleties. We'll be talking about all these gates, Pauli matrix, Hadamard, and C0 in the next slides. And then you'll get some feeling about it. And then we'll be going to the codes on how to, first we'll be talking about how do you code a gate acting on a single bit with Python, and then something similar to the C0 gate. Of course, C0 gate is very important. So to teleport Alice's state to Bob, we will need Hadamard gate, which is here, you can see. We will need C0 gate, because these will create you the Bell state. And then we'll have to do some measurements. So these are very important, by the way. So you'll have to understand, if you don't understand these parts in the next couple of slides, you'll be lost. As I said about XOR gate, the classical gates can be reversible, no issues. Quantum gates must be reversible. And one more thing is classical algorithms work on 1 bit at a time, as you know. But in quantum computation and quantum mechanics support superposition. That's the most beautiful part, because you can perform operations simultaneously, and you can get something like, for some algorithms, you can get exponentially fast speed up. Even for classical problems, for example, factorization. Factorization is a classical problem. Imagine you want to factor a number which is 15. It's for smaller numbers, it's fine, but the computational complexity increases very fast as you go for higher and higher numbers. But there are algorithms like Shor's algorithms and other things, and they actually give you a literally very high speed up with quantum algorithms. So quantum algorithms are definitely very smart in that sense. Okay, so this is just a very quick refresher about the Dirac notation. I'm sure all of you are very well familiar, but just for completeness and anyway. So you know this is Kret, this is Bra, and this is basically the dual vector of this vector space, while A and B both live in the complex 2-dimensional vector space with a norm. I should say something like L2 norm. Yeah.
So
anyway. Yeah, sure.
Can I interpret? So
yeah, sure.
I had a question, and actually one of the participants already asked.
Oh, I see. Yeah, please. I don't see the chats. Okay, yeah. I can
Chat you
see.
can see.
What is reversibility and irreversibility of the gates? Okay, we will come back to this. We'll come back to this. When we will come back. When, as I said, that C0 gate is somewhat which is reversible and XOR gate is not reversible. While we will be going into the 2-qubit gates in 2-3 slides after this, we will be specifically showing you what do I mean by reversibility, and it will be very, very clear then, don't worry. And if I'm not telling, just unmute yourself and just speak up that you promised something and you're not doing that. Feel free, no issues. Or any of you can just unmute yourself and speak up. Okay, so this is the complex conjugate of this. As the star means the complex conjugate of this vector, the vector B, and bracket is there's the inner product of this stuff, and Ket-Bra is essentially somewhat like an outer product, which gives you the matrix like this. And right, you have to guarantee that on this space, your vectors are orthogonal and normalized. By orthogonality, I mean the basis vectors are, if you take the projections, right? So this is essentially the projections. The projections give you 0 on each of these bases, and the definitions 0 in the next and the next and the next and every slide. We are going to heavily use this notation 0. 0 is essentially this matrix 1 0, and 1 is 0 1. So do remember this. This will be helpful for you, because not in the following slides, we're not going to write it in the form of this matrix notation. We'll be using this bracket notation. And I think at least you guys should be familiar with this. Yeah, normalization is this one. And let's go to the next one. Measurements. As I said about the basis functions, etc. So what is a measurement? Essentially, it's a projection. And as I said earlier, that the basis of functions are orthonormal. So and they have to form a complete basis so that they span the vector space. These are some technical words. For now, you can forget them. But anyway. Remember that there are infinitely many basis sets available. These are only just 3 examples. These are the known Pauli matrices, by the way. So I said I defined what is 0 and 1 in the last slide, and so you can see that you can take a superposition or something like a linear combination of this 0 and 1 state, of course, with proper normalizations, and that will give you something like called a plus state. And if you do this minus, it will be minus state. If you do something like iota times this, you will get iota plus iota minus iota, and you call it sigma y, and this is the standard sigma z that I have defined in the last slide. And definition by this Born rule, x and psi mod of square, that gives you the probability, and definitely probability will have to be 1. Sum of all the probabilities will have to be 1. These are something that I assume that you all know. I just skip through very quickly. So let's now define something which is a normalized pure state. You can ask me what is a pure state. It's something that okay. It can be correlated. It may not be correlated. We'll be dealing with the pure states later on. Correlated. As of now, they are completely uncorrelated, but we'll be dealing with the correlated pure states later on when we'll be going to the entanglement. So for now, just okay. You don't have to go into this as long as you're not encountering the mixed states. And in this lecture, you're not going to. So feel free to go with everything with the pure states. I need to define this block sphere. This is something which is very, very fundamental to go forward. Okay, so let's so this is the state which is psi that I said. There's one quantum state which is a superposition of 0 and 1 with different weights, right? And this is a phase which is e to the power I phi, iota phi, and where phi essentially is close to 0 to 2 pi and theta goes to 0 to pi. So you can see this this represents a vector in this block sphere. So essentially this is a sphere, and you can see at different angles, theta equal to 0 and phi equal to arbitrary. This corresponds to r equal to 0, 0, 1 somewhere. And then this is something, the one state. So this is the 0 state, this one, and this is the 1 state, this one. This is the plus state, this one, minus state just in the opposite direction. So this is what is the block sphere. And just a quick question I thought I'll ask you to see whether you are sleeping or awake. What is the probability of, given this psi, what is the probability of finding psi in the 0 state? And similarly, what is the probability of finding 1 for this state? What do you think? Can somebody unmute yourself and tell me?
For state 0, it may be cos square theta by 2.
Exactly.
And for 1, it will
Yeah,
be
1 minus cos square theta by 2 sine square theta. Exactly, perfect. Thank you. Okay, great. So at least some of you are awake. Thanks for that. Okay, so I think these are something that you know, and let's go to the next stuff as promised. Well, as of now, we have not encountered irreversible stuff. We'll be going to see that in the next couple of slides. These are the single qubit states, as I said. This is something like the classical equivalent is something like the NOT gate, that given any signal, you just flip it. So for single qubit states, as I said, all gates represented by unitary matrices. So these are the 3 unitary matrices, sigma x, sigma y, sigma z, the Pauli matrices. They hold these properties that sigma I square equal to identity, and they form a complete basis set. This complete may need some discussions, but I'm sure you'll make yourself happy with your quantum mechanics classes, quantum mechanics knowledge, and you'll find some answer. This is something nasty, but anyway. This set 1, sigma x and sigma y, you can express any vector in this C2 space in terms of these vectors. That's what I'm saying initially. Okay, this is the Hadamard gate. So now you can see the matrix. This is the matrix, and this is the composition. You can express this matrix in terms of this sort of superposition. And there is one more state, one more gate that exists, which is this rotation. Just to give you a quick idea about what exactly these gates do, because all of you have probably heard very well about Pauli matrices. You may not know what does that do. So essentially, sigma x is this. This does a bit flip operation, which is equivalent to the NOT gate or classical NOT gate. And so if you go to this previous stuff, remember the block sphere. So what does it do? It essentially gives you a rotation around the x-axis by an amount pi. So you have seen in the if you have gone back to this, here you have seen 0 state was here, 1 state was here. So this is the angle pi theta around. This is the z-axis. So if I feed 0 to sigma x gate, it will give you 1. So this will essentially flip the state from 0 to 1 or 1 to 0. Okay. Similarly, sigma z causes a phase flip. It works on the phase of the state, which is essentially equivalent to rotation around the z-axis by pi. And sigma y, as you can see, this you can write in terms of multiplication of iota times sigma x times sigma z, which is a bit and phase flip. So as of now, there was these are very simple. There was no superposition. What causes superposition is this Hadamard gate. If you apply a Hadamard gate on a state, it creates a superposition. And the S, this adds a 90-degree rotation to the phase of phi. So I have to give you some idea about I kept some examples. I thought I'll skip this, but just to tell you, you know what is the sigma x, right? This is the matrix. The zero state is 1, 0. So you can just multiply it and you will get 0, 1. So this is the one state. So this is how it causes a rotation within the Bloch sphere. Similarly, if you look at the operation of sigma z on this plus state, you can do this, and then you can convince that this plus state will be minus state. I defined what is plus state. The plus state is 1 over root 2, 1, 1. 1 over root 2 because of the normalization. Similarly, Hadamard gate. So these are giving you actually the discrete rotation on the same basis. So this is bringing you from 0 to 1 or plus to minus. But Hadamard is something that is operating on 0 and giving you plus. So this is something like creating a superposition, as I said. So these are the matrix multiplication way. You can convince yourself and do this multiplication, and this is something similar. Instead of acting on 0, I just acted in them on 1. And you can see, if you look at the bracket notation, or the Dirac notation, if you try to do this is the same. I mean, you could have done it the same way in the matrix notation. Just to make you familiar with the Dirac notation, I thought I'll give you something like sigma x operating on 1, that is giving 0, sigma z operating on minus, that is plus, and you can try them out yourself by hand, operating h on 1 that to get minus and things like that. So essentially, as I said, h helps you to go back and forth between x basis and z basis. You remember the Bloch sphere, always remember the Bloch sphere, it will help you. And the S operator operating on plus gives you iota and minus iota. And if you can apply one gate simultaneous, just immediately after the other, this will give you S dot H. That will help you to flip between Z to Y basis. Now some coding. If you go to, so I'll be showing you one of the tutorials given on the summer school by the Qiskit channel. So they have created a very nice Jupyter notebook. So I'll be just going to the Jupyter notebook to show you. Before that, I just thought I'll tell you. So what you need to do is just pip install these resources. You can do the same on your terminal as well. I mean, from your editor. From IPython Display, you know this. And then from Qiskit, just like you do from NumPy or from Matplotlib, you import something, you can do from Qiskit import quantum circuit. And this will, so these are all the commands that I'll be using in the Jupyter terminal. I have just kept them in one slide. So now maybe it's a good time to go to the okay, let's complete, since the question was asked. So these are, you can see the Python implementation of the single qubit steps. So these are all single qubit. Since there was a question on the irreversibility, just let me go one slide forward and talk about the irreversibility. That will, remember, that will not be the single qubit stuff. I'm going to go into the 2 qubit thing. So there exists, instead of single states, there exists bipartite, where there are 2 states, or essentially, for more generally, multipartite quantum states. A cross B cross C cross blah blah. Cross means the outer product, not the A tensor. So this is essentially the full here it is a bipartite state. You can effectively have higher dimensions. And for 2-qubit gates, this is one of the examples, CNOT gate, as I said. You can see this is the matrix, just like the previous stuff. This is the matrix for the CNOT gate and this stuff. Why this is irreversible, and what is so special about CNOT? Let's look at the input. So this looks as a classical input 0 0 1 0 0 1 0 1. This is the table that we all did earlier in our bachelor's, master's. I don't know where you have, depending on which branch you are in. Forget about this X now. Just look at this X or Y. So if I give you 0 0, you get 0. If I give you 0 1, you get 1. If I give you 1 0, you get 1. So from this side you can go to this side, but if I give you the output which is 1, the input is degenerate, right? Either X can be 0, or I mean, if X is 0, Y can be 1. So if I give you the state which is 1, you can't say whether it has come from this input or this input, right? Something like, I don't know, I don't remember the term, bijective, 1 1 on 2. So this is something like many to 1 on 2. Probably not bijective. I don't remember. Anyway, so this is the classical stuff. Let me note it. So this is the classical stuff. Sorry. What happens? This is the classical. And if you operate the CNOT gate, just remember to copy this X here. So this is the whole output of the CNOT gate. So this is the whole, sorry, yeah, this is something essentially called reversible XOR. XOR is in general the classical XOR that is not reversible. So if I give you the output of this much information, if I give you just this is irreversible. But if I give you this whole stuff, this is reversible. Yeah. This whole information. This is now given this 0 1, you know where from it has come here. Given this 1 1, now you know it has come from 1 0, and given this 1 0, you know it has come from 1 1. So this is what I meant by reversibility or irreversibility. Yes, this is very important, because remember, all these operations will have to be unitary. That's very important. Okay, now let's go back. What happens? No, I don't want this. I have to quit from here. Okay, let's just go one slide maybe. Oh no, I did not. Sorry. Okay, just a little bit of so this is a homework given on the tutorial there. This is you can just go to their Qiskit website and go to the summer school or something. This is the first homework essentially, actually. First lab or first something. You just go and just open it. So yeah, installing necessary packages, as I said, install stuffs like that. And then for single qubit states, suppose you want to initialize a state which is 1 minus p. P has some values. And how do you do that? So first thing is from Qiskit import quantum circuit. And this thing. The above quantum circuit does not contain any gate. As you see, this is just a circuit. There's no gate I have applied. Now, you can try to see which state it is from. You can do this SV, which is import the state vector, and SV equal to state vector from level 0. You can look at the data of the state vector just like this, and then you can evolve the circuit. It does not do anything. Right. Let's come to the sphere. You can have a very nice visualization for the block sphere. And right. So this is you have initialized a state at 0, 0 0. This is a single state, so that's 0. With some phase equal to 0. You have not performed any S gate operation on this. So this is the red color. The color is important, definitely remember this. And now you're going to apply some gate which will flip this, flip or do some operations. to bring this state vector from here to somewhere else. And the size of this thing also matters, because this gives the probability. This is now on 0 state, so this is the highest probability of 1. So when if you have something in the something like 0.5 times 0 and 0.5 times 1, then the size of this will be half. The size of this blob will be half, is one thing. And the other thing is, if you add a S operator on that or some other thing that adds a phase to this, you will see the color of this blob will be changing from red to some other stuff depending on its phase. So this is the circuit. You can do some applying an X gate that flips qubit 0 to 1. Then you can see. So one way is to visualize it within this blob sphere. The other way is to visualize it like this. So if you had this 0, which is 1 0, and now this is 1. If you do this my circuit dot x 0, so this dot x means you are applying the X gate on this circuit, and that gives you X means the sigma X essentially. So this flips the phase and then gives you 0 1. Right. So earlier it was 0 here, 1 0, and then on this state you apply this my circuit dot x. My circuit is the quantum circuit 1, which you have imported here. Yeah, my circuit equal to quantum circuit, and then you initialize the state here, level 0, this one, and from. Can you see my cursor? I think. Otherwise, what do I mean by this and that? Can somebody just unmute yourself and just speak up that yes or no? Can you see my cursor here?
Yes.
Okay, great. Thanks.
Yes, sir.
Thanks for confirming. Okay. This is essentially the flip operation that I said. So now you can see the phase has got flipped to 1 here like this. And similarly, we can create the state which is a superposition of 0 and 1. So what do we do? Again, let's take the 0, so initialize it to 0 and then put it in the circuit and use a Hadamard gate. So this my circuit dot H is essentially a Hadamard gate, this one. Okay. So this is something that is operating on this 0 state. 0 means this 0 1. Sorry, 1 0, this one. You are operating a H on this state. So let's go back to, H operating on 0 should give you the plus state. So this is the plus state. Now if you plot it in this Q sphere, you can see this is the plus state. Just half on this and half on this. Similarly, you can see this. Yeah, so this is essentially 1 1, right? This plus state is 1 1. Okay, and you can add some different phases and things like that on this one, etc. You can play with this, and there's an interactive tool like this. Here you can see. So let's try one of the examples. Let's do just this one, H and 0. So this is the 0 state. We know the example, right? It gives you this state. So let's apply H on this state. You see, it has got into a plus state. Okay. You can apply a phase on this. Okay, this is single qubit. I can't show you the CNOT gate now, but you see the phase has got changed. It is now a different. And remember, if I go to the reset, so this is bigger in size. Right? So this is 1, essentially. The probability of finding this in this state is 1. If we apply this H gate, the size gets shrink, because this has now 1 over root 2, 1 over half of that. And if you add a phase, it's just a phase. So essentially, there is no change in the probability. is in the e to the power iota 5. So this is the z-axis. If you want to rotate around some other axis, okay, let's not do this. The big list is given here. So you can initialize a state like this, and all the operations are given. For example, if you have a state which is 1 like this, you operate an X gate, it will flip you here. Instead, you can operate a Hadamard gate to go back and forth between these two. You can operate a Hadamard gate to back and forth between these two. You can use the S gate and S inverse gate to go back and forth like this. You can use the Z gate to go from here and all this stuff. So these are some basic single qubit gates. And it is such a nice tool to visualize, to see what is it. And believe me, these are something that are real, because we are going to create one state in the future. We are going to create today only, create a state which is in the superposition of this state and this state. And we are going to teleport that today on a real quantum computer, not on something which is a simulator. So I'll be connecting. I'm already connected to to my IBM account, and I'll be launching the job from here through my classical computer using my classical internet. That will go to their portal. We will launch the job. That will go into that one of those pictures that I've shown you earlier. One of these machines, they have multiple such. So, and they are probably gold plated or something. But anyway. So, and then it will be executed there. The qubit will be actually transported, what is that? Teleported. And then we'll see several times we'll perform the same stuff, and we'll find the probability with how much accuracy things have got executed or not. Okay, the next thing is that multi-qubit state. We will need this because to create the Bell states, we'll need this multi-qubit states. So this is something that you initialize the state at 0, 0. So we have now 2 bits. As I said here, here, this is essentially the outer product of 2, 0, and 0. Now you can think somewhat like 0, 0. This stuff, this 0, 0. Here, so this is the star, and you can see there is a because this has 2 states, you'll have several other things. Okay, so now the CX stuff that you can see here, this is essentially the C0 gate. So here what they're doing is, we'll go to the next slide and then we'll learn that, and then we will again come back to this. Remember this picture, we are going to look at this. This is something that we are going to use very heavily. This is the Hadamard gate and this is the C0 gate. So this signature sign is the C0 gate and this is the Hadamard gate. As you can see, this is Hadamard gate because this is a single qubit gate acting on a single qubit, and C0 is a 2 qubit gate acting on 2 different qubits, and these are the 2 qubits, Q0 and Q1. Let's go. Entanglement. Okay, so as I said, I will come back to the definition of pure state. Okay, I'm not going to come back to exactly the definition in that sense. I'm going to restrict myself in somewhat simpler things. If a pure state psi AB, 0, 0 is one of them, of a composite system A and B cannot be written in as a direct product. Earlier we have written it as a direct product like this, right? Because if I go to the previous slide, if you see this, we have been able to write it as a direct product. So now I'm saying if we cannot write it as a direct product of the component systems like psi A and psi B, it is called an entangled state. Few of the examples are these Bell states, which are maximally entangled state on orthonormal basis. So these are few of the examples. So you can see this is 0, 0 plus 1, 1, and this psi 0, 0, you cannot write it in terms of like psi A times psi B. This is not possible. So these are the maximal, these are called the maximally entangled state on the orthonormal basis. And for all these 4 states, you can sum them up somehow, and then you can write it in terms of something like this. Okay, so remember this notation. This is something that we are going to use. Right. So you now remember this, right? As I said. So this is suppose. So let's go back to the previous step once more. I said A and B as psi A and psi B. So this is important. I'm going to start with 2 qubits, IA and IB. The next step, IA and JB. Sorry, yeah. And I'm trying to entangle these 2 states using these 2 gates, Hadamard gate and a CNOT gate. So the initial state is IJAB, which is this. And if I act a Hadamard gate on any of these states, I and J, we get something like this. And this is still not definite. This is just a superposition of 0 and one of these. And then if we add a CNOT gate on this, I showed you the matrix notation of the CNOT gate earlier. If you do this, then you get the Bell states. So these are the 4 Bell states. And so this is the mechanism of creating the Bell states from the initial state, IA and JB. Okay, why is the Bell states important? Because to teleport one state, we will need the inverse operation of this Bell state. So this is why I'm telling you Bell states. So, right, so this is the entangled state that we finally come up. So, and for the coding, you can see the H is the just H on Q0. So this is the Q0, you can see here, Q0, H acting on Q0. This gives you these states. So that means writing in the compressed notation, it will be like this. And then if you act a CNOT gate on from Q0 to Q1, because this is a 2 qubit gate, as I said, this is not a single qubit gate. If you do this, that means this operation, this one, which is basically this thing. And if you write it in terms of the matrix notation, you'll be able to come from here to here. This finally, for the final stuff, gives you the psi JAB, which is this. And okay, and let's go back a little bit to the Jupyter notebook. You can see this is just a different notation, my circuit .h, or if you're going to use this other thing, you can do this. Anyway, so this is 0 and 1, then you can draw the circuit. Now you can see these are the I have plotted the state vector here. So these are the entangled state 0, 0 and 1, 1. Okay. And if you make a measurement, if you plot a histogram, you see roughly there half they have the probabilities 0.5 and 0.482. Okay. Measurements. Okay. Now you can also do a measurement, right? If you do the measurement, you do the measurement like this. If it is this measurement, you get these things. So you can do these are the probabilities, roughly 0.5 for both of them. For quantum teleportation, we'll go here. Before that, I wanted to show you this, how funny they are. I can just simply press delete and then just delete them. So now you can see there is nothing. I can delete these stuffs. Okay. I have Q0, and all I need to do is, if I go, this is the IBM Quantum Composer. It is free to all. You can see it on your house. You can use it from your mobile also, not necessarily from your laptop. You can log into your IBM Quantum Composer and then just click on it. I have now clicked on it and hold it and drag it just like this, drag it and drop it. I dropped it. And you can see here, earlier it was 0 because Q0 was in 0 with the probability 100%. Now, if I'm applying a Hadamard gate on this gives me, if I take it here, state 0 with probability 50%, and here state 1 with probability 50%. In the Q sphere also, it gives you the plot immediately. State vector, you can see it like this. You can see the output state with the probability. 0.707 is the 1 over root 2, value of 1 over root 2. Okay, and then I mean, if you don't want that, you can want some other state. I don't know, anything that you want. Just suppose it's y. It took you from 0 to 1 just here with some phases. So you can do anything. I just wanted to get the Bell states. So to get Bell states, I will need H like this and a C0 gate. If I drag and drop the C0 gate like this, oh no, this is not right, because C0 will have to operate on, it says error in QASM82. So this is an error, definitely. I will need one more state because C0 is a 2-qubit gate, as I said. I will need to bring this C0 gate from here and here. If I put it right here, now it has created the famous Bell state, one of the Bell states. You can see that H operating on 0, CX operating on 0, and Q0 and Q1. This is, and you can put some barriers like this to show like this, etc. It does not change anything. So this is basically the picture that I have shown you, but I thought this drag and drop stuff will you appreciate, some of you at least. I like this, but anyway. Okay, let's go back. So we were here. I'm just going to very briefly, I'm just saying whatever we have already viewed in the last Jupyter notebook. For 2-qubit states, I have just kept them in like this, 0, 0, and operate to get this entanglement, you operate H and CX. These terms, evolve them, and these are the things that we have already shown in the Jupyter notebook. I just kept them here as a concise format. And here we are now ran it in the backend was we ran it on the simulator to get you. I've shown you something in the 50-50 probability, right? So that was not a run on an actual. Okay, you said okay, okay. That is not run on an actual quantum machine or quantum computer. So that was a simulator that I ran. But now I'm going to, within a 10-15 minutes, I will be explaining you and showing you running it on an actual quantum machine. But before running, I have to tell you what I'm going to run and why. So I'm going to teleport a state which is phi. So this is something when people in US or Europe and other English-speaking countries, they write it always as Alice and Bob. In India, they call it Rams wants to send something to Rahim and things like that. So anyway, all our earlier school days examples used to start with like this. Anyway, so the goal is this. Alice wants to send her unknown state, which is phi, which is a single qubit state, which is a superposition of 0 and 1, and with some alpha and beta. I don't know the values of alpha and beta. So this state is somewhat like indexed. Just to keep track of this, I just say it S, 0S and beta S to Bob. However, she can only send in 2 classical bits. Okay. And they both share, this is one more thing that is given, that they both share maximum. So this is maximally entangled is basically one of the Bell states. So now imagine this is they share the 0, 0. They can share some other Bell states as well. But for now, just you can do the whole calculation here. So they both share maximally entangled state, which is size 0, 0. So this has Alice has some copy. So A for Alice and B for Bob. And this phi is the state that needs to be teleported from Alice to Bob. And this teleportation will happen only with 2 classical bits. So Alice can send only 2 classical bits to Bob and Bob will have to reproduce this phi s, this state. So the problem is like this: Alice and Bob share a maximally entangled state psi 0, 0. Now Alice, suppose, is in Earth, Bob is in Moon, or I don't know where, anywhere. Ideally, according to the quantum theory, he can be anywhere in the universe. But the problem is this quantum decoherence, as I said at the first. Earlier, we have seen that at max we can send it 5 kilometers or so. When we are in masters, then we learned that people have been able to teleport it in hundreds of kilometers. Now I see people have been able to teleport it in thousands of kilometers on different satellites and things like that. Yeah, just 1 hour, 10 minutes. Okay. Okay. And now, so essentially, Alice needs to send the 2 classical bits from Earth to Moon, suppose, and Bob will have to reproduce. Bob does not have this phi state with him. Bob will have to reproduce this phi state just with Alice's information on the 2 classical bits. Okay? Okay, so the initial state of the total system, phi s, outer product of this full entangled state, this one. So these subscripts will help you keep track. You can do this outer product in the bracket notation. I gave you some examples, the slides, to make you habituated with the bracket notation. This is alpha times, yeah. So this is basically just you multiply this stuff. Now you can show, you can do a little bit of algebra, and you can show that you can decompose it like this. This is a state that you cannot write as a pure tensor product of 2 states, but these are the states that you can do. Okay? These are not the Bell states. Okay, so this is different. SA, this part, and this is a superposition times this is the Bob state, this part. And these are different combinations, all 4 combinations. And then you can recognize them as phi, because this is alpha times 0 plus beta times 1. But these are in Bob's end now, this one. And now if you make a measurement, you'll get a probability of, you'll get which operator to operate. So let's look at this. And I know this is not very clear, so let's look at it in a much more detailed way. Okay, so this is something I just copied. So this last line, this one equal to something like this. This is an algebra that you can just make yourself comfortable with. Later on, I will post a slide somewhere. And after all the dust of algebra settles, you can just take this. I have just copied this last line in the next slide. Here, this one. Okay. And we will see how exactly it works in the circuit diagram. So now you remember the Bell measurement, right? Because this is something that I'm not explicitly showing you the circuit. Maybe in the next slide. Yeah, here I have explicitly shown this circuit. This is just the inverse of the Bell measurement, of the Bell creation of the Bell state. So at the time of creation of the Bell state, we had H and then this C0 gate. Now it's just the opposite. From the output part, you take the C0 gate, then H, and then do the measurement. This is called the Bell measurement. Okay? So this is this part. So Alice has a state phi s, which is this one. And this is the maximally correlated state of Alice and Bob, which is psi 0, 0. And now what Alice will do, Alice will perform a Bell measurement that we have already seen in the last Jupyter notebook. And so what is one? Alice performs a measurement on S and A in the Bell basis. So Bell measurement is that one. What will go here? One. So this one is this one. This one is this one. Alice's measurement. Psi 0, 0. So there can be several combinations. Psi 0, 0, 0, 1. Time the outer product of this phi s. So if you do the Bell measurement, the output you can see psi 00, this is essentially SA here, subscript, phi B, this one, this times this, plus psi 01 SA, outer product, sigma X operating on phi B, sigma X operating on phi B, plus these are all possible probabilities with some depending on what is the values of alpha and beta in this phi S. Okay. So these are different combinations. This stuff is essentially, you can see this stuff. So you can write it as a linear combination of this outer product, this plus this outer product, this plus this, and so on. If you do this Bell measurement, what happens? The 6 cents are classical outputs. So if you do this measurement, you'll get some classical output in terms of 0 and 1. Right? So in this I channel, you will get either 0 or 1. In this J channel also, you'll get either 0 or 1. So when I'm saying 2 means this, both of this here, you are suppose. So it sends her classical output ij to Bob. So if it is in this state, in the first thing, in this state, this one, you will get 0, 0. So this is 0, 0, this one. And then 0, 1, if it is on this state, this part. Yeah. And then here you will get 1, 0, here you will get 1, 1, for this. So Alice sends this information with some probabilities, alpha, beta, depending on the values of alpha, beta that is seen in this file. So Alice will get this ij values. And Alice sends this information of ij to Bob, and Bob performs this operation. So this is the 3, here this is 3, this is 3, and this is 3. So Bob applies sigma z to the power I is this value, Alice is I, 0, 0 or 1, and sigma x to the power j, sigma z to the power I, sigma x to the power j, j is these values. If Bob applies these stuffs, he will get back 5. Okay? So sigma x to the power 0 is identity, sigma z to the power 0 is identity. So this is identity. And now you can see sigma x to the power 1, here 1 is sigma x, sigma z to the power this is 1. So identity into sigma x is sigma x. So similarly. And if Bob applies these gates on this psi 0, 0, so Bob also share this maximally entangled psi 0, 0. If Bob applies these gates with these powers, Alice's information of ij of these powers, he will be able to reproduce the phi b state, which initially Alice had, this phi s. So this is now a copy of this phi s state. Now you can ask the copy, what do I mean exactly by a copy? It's not.
Oh, so sorry, the protocol was, sorry, I missed it. Protocol, was that the protocol was they will share maximally?
That's what I'm saying. I said this is very important. So Alice and Bob will have to share this maximally entangled one of the Bell states.
Oh, okay. And this is the state that you have written at the top. It is being in the basis, Bell basis?
Right, it's in the Bell basis, yes.
Okay, yeah. Thank you.
And right, so but you have to remember, what do you mean by copy? As I said, Alice's state collapses after measurement. So, there's a theorem called no-cloning theorem, which is essentially guarantees that you can't make a copy of the state, but the information you can send from Alice to Bob. And also you can ask that if they are to different parts of the universe, definitely Alice knows, once Alice makes a measurement, Alice knows what is there in Bob's hand. But the information will have to be sent via these classical bits. These are the classical outputs by this. They propagate at the speed of light. So there is no violation of causality. Now we'll see the actual code. So the purpose is to teleport the quantum state. Now imagine this is 5s, okay? With these are the alpha and beta, alpha 0 plus beta 1, so 0.7 root of something, something. So teleport this quantum state from Alice's qubit to Bob's qubit. First, you need to initialize the qubit. Definition: initialize qubit given circuit, and you have seen import numpy, blah, blah. Circuit initialize with 0.7 and 0.3 qubit index. You have 0 and 1. And then you have to perform bells. You have to create a bell state. So you have to entangle two qubits. So now you know how to entangle the qubits, right? You know the Hadamard gate. You know circuit. If you do circuit dot my circuit or given circuit, whatever, circuit dot h will cause the Hadamard gate. Dot cx will cause the CNOT gate. So the final output of this function, which is def entangle qubits, will give you a size 00 or size 01 or whatever in the previous slide. Now you need to make a bell measurement, as I said. So sorry. So this is something I'm talking about, the creation of this size 00. Okay. So initially I prepared this 5s at the superposition 0.7 at 0.3. Here you can see square root of 0.7 and 0.3. Here I have prepared the bell state size 00 or size 01, one of the bell bases. I haven't done any bell measurement. Now this is bell measure Alice's qubit. So to measure the Alice's qubit, now you know how to measure, right? You know, first you have to apply a CNOT gate on this bell state and on this 5s, that is the Alice's state. So you do it on qubit 1, which is this one, Alice. Qubit 2 is this one, basically this one. And you do a CNOT gate between these two, and then you do an Hadamard gate, which is on qubit 1 of Alice. This one, this is Alice's qubit 1. Okay, apply a Hadamard gate, and then barrier is just to show you properly. And then you'll have to measure. You'll have to make two measurements, which will give you the classical output 0 and 1. So you do circuit dot measure on qubit 1 and on qubit 2 on this Alice state. Okay? As simple as this. So here I have said something like beta 00. So this part is this function, this one, entangle qubits. You have to create this state. This is not freely available. So to create this state, you first need Hadamard gate and then CNOT gate. I showed in the last two, I don't remember that, how to create entangled states or bell states. And this is an initial. So these three functions are now clear. Now we have to do two measurements depending on Alice's output. Right? So define the function controlled operations. Controlled because these are controlled by Alice's outputs. Okay. On Bob's qubit, on Bob's part of this this maximally entangled bell state. So this is a measurement on this x and this is on z, because you have seen you have to do sigma x and sigma z operations, right? So given circuit dot x, given circuit dot z. So this is the sigma x operation. This is a sigma z operation. Now to the power something that comes from here. 0 or 1, depending on what Alice sends. Okay. So these are basically the output of Alice's operation. These are this after this M1, what is going out from here. These things will actually enter into this function here, this here, and this is 1. They will define whether it is 0 or whether it is 1. And now, so you have all the bits of the functions now available with you, and now collapse, call all the appropriate functions, and you are ready to launch your run. Import Qiskit from quantum resistor classical. You have classical resistor here because you are sending 0 and 1. Set up the qubits and initial bits. So So this is the initial, just these 4 stuffs. So here I write the quantum teleportation circuit, initialize. So this one, initialize qubit. Initialize qubit, call this function initialize qubit, my circuit on 0. So these are all starting at 0. And so this is this one, creating this, which is this function. Then entangle, create this part, this beta 00, you have to create it. Entangle qubits, which is this one, entangle qubits, this one, my circuit 1, 2, so this part. And then do a Bell measurement, this one, do a Bell measurement. So here, this is the Bell measurement, this full part. This is the Bell measurement. Bell measure Alice qubit, this yellow one. Bell measure Alice qubit, call this one, okay? Very neat. And then put a barrier. And then these are the information that comes out from Alice. Apply classically controlled quantum gates. This is the part basically. Controlled operation Bob qubit, this part. Controlled operation Bob qubit. And do all this. And then you can just draw it. If you draw, you will see this circuit diagram is coming out. And once we get this circuit diagram coming out, we'll launch it on the quantum machine. Ready for that. Okay, so let's go back. This is the graded exercise. This is the code that I've taken. Very simple. This is the solution of that. This was an assignment basically on the school. This is the solution of the assignment. It was given as an assignment in the summer school. I'm not doing anything great or anything, something just very difficult or anything, and something which is a research stuff. It's something like a very simple, basic teaching stuff, but probably very funny. At least for some of you who don't know, who know, definitely it's boring. But anyway, so if you do this and then if you ask to draw this circuit, this essentially is this circuit that I have already drawn here. You've seen this circuit. This is basically the same circuit, and you can just check whether everything you have initialized appropriately or not. And then you go to this. I've already run it yesterday and today, just before the lecture, I checked running it, whether they are right or wrong, but we will run it again. Okay, so here you can see the same stuff. Initialize the state, then apply a Hadamard here that I've said to create the Bell states. Yeah, to create the Bell states. And then, this Q0 is basically, if I try to open this side by side, here, I hope, where should I put this? Now let's go back one more slide. Right. Q0, this one. This is phi s that I've seen, Q0, alpha 0 plus beta s. So this has been initialized with some random state, I don't know, something that anyway. So initialize this set with alpha and beta. So these are the values of alpha and beta, and then you create this state. This one, psi 00 AB, Alice Bob, that Alice and Bob both will share this part. So to create this Bell state, you need Hadamard and C0, as I said again. These are the barriers to everybody. And so that one is not performed earlier to the other. And then you do Bell measurement here. This part is the Bell measurement in the next slide that I've shown you. This stuff, Bell measurement here. This one, and then you do measurement. Okay, so that's not written here. Okay, this is the measurement, and then you send the information, and Bob applies its the appropriate gates depending on the output, and then disentangle into the measurement and get the stuff. Let's go to the right. So this is basically the same thing that you have seen. Alpha 0 plus beta 1, it's the repetition of the stuff that now these are things that we already know now, just written in a different notation. Right, Hadamard identity, then C0, etc. You can just go through this. these are the things that you have seen here. Right. Bits received, bits received is this 0, 0, 0, 1, 1, 0, and 1, 1. Then get applied is identity sigma x, sigma z times sigma x, this one. Okay. And if you do that on a teleportation on a real quantum computer, IBM hardware. So I do, let's do this kernel, clear output, restart, and clear all output. So I've cleared the outputs. So on the same stuff, on the same code, I just run it again, and then I want to see how the results are coming. Kernel. If I now launch this, so these are the previous two runs. Let's run it, restart, and run all cells. Sometimes this takes some time because the cluster remains busy. Many people simultaneously launch the runs. Yeah, this is the qubits. I'm just executing. This is the Jupyter notebook. I'm executing it once more. This now got. Here you can see the whole stuff. Descent angular. Right, job is queued, queue number 2. So pending. Okay, July 10. Currently my time is 10:30 a.m. in the morning. It's your 8 p.m. in the night in India. Okay, so I don't know when it will be executed. It's in the pending status. So it's in the queue for which machines. So there are different machines available: IBM Q Lima, IBM QX2, blah blah, depending on the architecture of the quantum computer. I mean, the way the network in which the individual bits are organized. So not all the bits are connected to all the other bits. I mean, not all the qubits are all connected to all the other qubits. As you can see, if I go to this picture earlier, here, not every qubit is connected to every other qubit, for example. So they have different topology of orientation. So this describes which way each of the qubits are connected to other qubits. So this causes different architecture of the machines. Well, it's still pending. Job is queued. Right. We have no other way to accept waiting, but we can look at one of the previous runs. Suppose this, by the time when it is. Okay, so I think I created. Yeah, if I go. Oh, running. Wait. It's running. Job is actively running. It's changed. Let it run, and then it will give us some result. Completed. Okay, now it has got some results. So this is the error. You can ask me why this much error has happened. Yeah, it's an active area of research, and not all the qubits are very noise free. As you know, we can't create exact ideal zero temperature. So we have launched a few thousand of, I guess, qubits and teleported them, and with 77% accuracy, we have been able to reproduce the same qubit in Bob's end in that quantum machine, and with 22.5% accuracy, we could not. So this is the error, and you can go to a detailed report of this. Yes. So it ran on 10:33 a.m. in 2 minutes 15 seconds. It got completed. It ran on this machine, IBM QX2. Right. It got validated. It was in queue for 1 minute 50 seconds. It ran for within only 22.7 seconds. Completed 10:33. Right. Number of shots is 1024, and you can see measurement outcome with somewhat like 794 times we have been able to reproduce it correctly in Bob's end, and 230 times we failed. And as I said, why did we fail? Because not all the qubits are noise free. So sometimes when you send some signal, there can be some problems. There are a lot of noises depending on how much traffic is there in the machine, and what is the local situation outside. All these stuffs do matter. So, but I was lucky. Last time, yesterday when I ran it, it went really well. You can look at, I ran 1024 shots, and I was very lucky. I got 980 times I got correct results, and only 44 times I got wrong results. So that's a good thing. Out of 1024, 980 times I could actually send a qubit, send a state from one place to another perfectly. Okay, that's what I said here. While today morning the result was really bad, now it's better. Today morning I checked it just before the lecture. Only 618 times I got correct results, and 406 times I got wrong results. So anyway, it depends on several things, mainly how much other runs are happening, etc. And these are free stuff. So okay, so that's, I want to show you the animation. So I'm going back. Yeah, fancy animation. Yeah, so the whole code that I've shown you, that's free and open source. You can go to this website, log, the whole stuff is there already. And this is the result that I got yesterday night. So I got really good accuracy, and so I thought I just took a screenshot and I've pasted it here. If you go here, you will not be able to run. You have to create one IBM account. It's free. It's for one, open for everybody, as I said. You don't even need to have a PhD degree for that. It's open for anyone. You can open it. You can create your account and just go to your IBM Quantum Lab and just do whatever I've just done. I did not do anything which is great. It's just the most trivial thing that a school student can also do. There is nothing great in it. Very simple. You can also do this. These are all run on Python. You can see this is running on Python 3, on this, powered by this Jupyter notebook. And yeah, this is a very nice, helpful stuff. I'm not aware of any other portals that give you such a flexibility, such open access to any user who can do real quantum teleportation, or all your algorithms, quantum algorithms, whatever you are coming up with, just write it in your Python, obeying this, using this module, their modules, etc. And you can actually execute it in those machines, the true quantum machines, and get your results and publish your results. They're really good. They're really helpful. Okay, and yeah, I just, as I said earlier, I just Googled this thing, maximum teleportation distance in experiment. It immediately, just in Google gave me 1400 kilometers. Earlier it was just a few hundred kilometers, but this is really amazing. So they have a satellite called Messias satellite, and they could actually perform video conference call between the Earth and the satellite. So this is something funny. And when I just Googled it, I finally found this thing. This is probably people ask, how long would it take to teleport a human? Okay, so this is a intriguing question. This is very interesting. Definitely, for many people think like that, but be aware. Whatever this 1024 shots we have done, these are the things where we have teleported a state, not any matter. We have not teleported any matter from place A to place B. We have just teleported a state phi from Alice to Bob. So there is a subtle difference, and you have to appreciate this. Don't just get lost into this words or anything. Okay, so yeah, you have to always be very much deeply rooted to the mathematical expressions and these things, because otherwise there can be confusions, fundamental confusions. Okay, if you have learned something new today, please go to menti.com, use this code and give me your feedback. I just thought I will just use this. This is the same thing that I used last time. You were awake, you were sleeping. Let me know whether you are awake or you are sleeping. Okay, that's it from me today. Any question or anything that you have, feel free to speak up. If there's anything in the chat? No, okay, sir.
So questions from participants?
Yeah.
Please unmute and you can ask.
Yeah, sure.
Sir, how can we use quantum lab, which is provided by IBM for research?
I think you can just write to them. I'm not a part of them. I'm just as I said, I'm just an amateur person in quantum computation. I'm not doing any formal research or anything. I like it, so I just Googled about quantum computation and I found something. I learned from there, and I think they are very open. If you just write to them, they will, for the access, definitely it's open to all. You don't have to do anything. You just open just Google about IBM Lab and go there, write your name, email address, and things like that. They'll give you an IBM ID.
It
and you
depends upon what kind of research one tries to do.
Right. So if you need something which requires a lot of memory, not something like one machine or something like two machines, you need to do some computation with, suppose, several qubits. They have a limitation, like for the free for free they have, I guess, 12 or 16 qubits they have. If you need to factor, suppose a factorization problem, which is if you need to factor a number 15, you can do that. But if you need to factor a number which is bigger than 15, definitely lower than the maximum limit that I already have, for something like 100 or so. So then you'll have to probably request them for more access or something. It depends. You can write to them, and if they agree, if your research, your idea appears important for them, they will give you the access as well. But I guess they're very open to public. Yeah. They're very open-minded, and hopefully, I'm not in any way personally connected with any of them. I have some while learning these things, I got some ideas and something, and I thought this I'll just do a little bit of testing in the machine. I was doing this, and I see that things really work very well. Of course, there is a limitation by this noise, but especially I really like I'm not sure whether you have heard of this called quantum Fourier transform. So initially the idea came from, so there is something called the searching algorithm, which are very expensive computation, according to the classical computation. These searching algorithms are, do you know something? What is the searching algorithm? For example, you have a string of numbers and you need to search one single number, how many times that appear or anything like that. These are something which are very expensive when you do a classical computing, because at every point you have to check whether it is bigger than that or lesser than that, whether it is. So it's essentially it's an if statement, and if statements are always very expensive. While in quantum computation, there are algorithms, for example, Grover search algorithm. And those are really good. I mean, those algorithms are something like enhancing the probability of one marked element and things like that, essentially, by deflecting it many times around the average and flipping it. And yeah, they are much more faster. And from there, people have now developed, for example, Peter Shor. He developed an algorithm called in 1990s, or probably in the early 2000s. Source algorithm for factorization. And once this, so for example, as I said, given a number 15, you can now, of course, you know that it can be factored into 3 and 5, 1, 3, 5, 15. But given a bigger number, can you find what are the numbers who are conjugately prime? Who are the biggest prime numbers that are coming out from it? For example, all this cryptography and everything are basically related to this. You have to go into the internet and make some searches. So cryptography, how are they connected to these prime number generations? And these are very funny things. Anyway, so one need a fast algorithm that gives us these sort of numbers, which are the prime to each other at least. Can we factor how big numbers you can produce, etc. And yeah, so this is one thing. And from